where you can make your code feel a little bit like art.
New frameworks, new standards. Things are changing so fast. You're always learning. That makes me happy.
For me, it was really fascinating when I discovered what programming actually is. When you make up an algorithm in your mind, you could execute it yourself with pen and paper or just by thinking hard. This is truly exciting.
It's really creative. Once you get the hang of it, you can create so many different ideas. It's really impacting the real world.
Every software is an artistic project. Since the first day I saw a line of code, I fell in love with Java programming. It's something on which I love so much.
I'm not sure if I've lost myself in coding or it's who I've always been. Coding definitely is going to get you once you type your first successful LOL. You can do and undo whatever you want, and makes me want to do more. Obviously, I sleep less, I code more, and I'm delighted when every time my customers say they're happy.
It's a very creative activity. If you ask an artist or a singer, why do you sing, or a musician, why do you write music? For me, I'm an artist, I'm a musician of my profession.
One way of looking at it is that code is another form of communication. With Sonic Pi, the goal is to explore the potential for code with music. Can we get anybody, not just musicians, everybody making some kind of crazy beats and sounds by writing simple lines of code?
Once you get your code run, the feeling is awesome. You can achieve anything within your imaginary with coding.
That's why I wanted to code in the first place. Create something brand new that hasn't been seen before.
Having imagination to build something beautiful and efficient, beautiful and usable. It's freedom.
Please welcome Greg Pavlik.
All right, hello, welcome to Code One. I'm excited to be here. My name is Greg Pavlik, so I'm a Senior Vice President here at Oracle. I'm responsible for our data management, artificial intelligence, and developer services on our Oracle Cloud infrastructure. We got a number of great speakers today for the keynote, so it's going to be a great series of talks. So first up is Dr. Kirk Bourne. He's a principal data scientist with Booz Allen Hamilton, where he focuses on the application of data science and machine learning to a variety of disciplines. Works across industries. Previously, Kirk was a professor of astrophysics and computational sciences at George Mason University. And since 2013, he's been one of the most recognized influencers on social media around big data and data science, digital tech overall in the industry. So Kirk today is going to discuss data science at the intersection of emerging technologies. He's going to show us how you go from data to insights to action to value. So without further ado, let me invite Dr. Kirk Bourne up on the stage to join us.
Twitter fans in the crowd, thank you so much. Hello, OOW19, hashtag OOW19. So glad to be here, so glad for this opportunity. Thank you, Oracle, thank you, Code One, thank you all for being here this afternoon. So I'm going to talk about this topic, which is near and dear to my heart. It's a four-letter word, and I use this four-letter word often, so I hope it doesn't offend you. The word is data. Talk about data a lot in my life. I use data a lot in my life. But see where this starts. 49 years ago, imagine 49 years ago, oh my gosh, I can't even think that far back, but imagine 49 years ago, a 15-year-old high school kid who had a vision and a dream to become an astronomer, an astrophysicist, ran across a book that was basically just tables and tables of tabulated data. Data giving the positions of the stars, the planets, the moons around the planets, the sun, the moon, all these things, eclipses, all these events, all tabulated when and where and how. And there was equations in the back of this book explaining how they derived these numbers. Well, I was just probably my first real experience with data, like hundreds of pages of numbers as a person who loved numbers and math to begin with. Seeing all these numbers, seeing this data as sort of the basis of science was really inspiring to me. But then to see there were mathematical equations that were related to this, i.e. there were models related to that data. And crazy enough, my high school at that time, 1970, yes, that's how old I am, got a connection with a 110 baud modem to the local university computer, where we actually learned Fortran, and I learned how to code those equations, and for the first time in my life, I knew exactly the path that I was on. It was science, it was math, it was data, it was coding. And it hasn't really diverged much from that in 49 years. Now, yes, I've had a few jobs along the way. I worked with the Hubble Space Telescope. I was the archive project scientist for the Hubble Space Telescope at Johns Hopkins University for 10 years. I worked at NASA as a contract manager, managing the astrophysics data system for 10 years. I was professor of astrophysics and computational science, as mentioned, at George Mason University for 12 years. But guess what? During all those 12 years as professor of astrophysics, I never taught an astrophysics course. I taught data science. We started the world's first undergraduate data science degree program 13 years ago, because the reason I left NASA and the reason we did that program is because it already became clear to me after 2 decades working at NASA with data, both as my day job and my night job as an astronomer, could see that data was not just growing astronomically in the sciences, but everywhere else in the world. And it became really clear that data was going to be the basis for every job, every profession. Every person needed to have some kind of aptitude, skill, or literacy around data. And I said, so I decided to leave my NASA position. I'll go to the university, and we formed this data science degree program to actually teach the next generation how to use data, what is data. And it was within a computational science program where we taught coding along with that. So along the way, more and more of my world diverged. I started getting invitations to speak at conferences about things I knew very little about, like healthcare conferences, national security conferences, smart energy grid conferences around the world. And I said, what do I know about this stuff? I'm an astrophysicist, but I know data, and I know science, and I know modeling. And so it's your gateway to all kinds of different interesting opportunities in life. And so the emerging technologies I'm going to mention today, and the amount of time I have, I can't talk too much about any one of them individually, but at the core of all of those things is that 4-letter word, data. So we're going to talk about that today, but in the context of this revolution that's going on right now. So you're probably familiar with this term. If not, I hope you will be now, and that is we are living through this 4th industrial revolution. Okay, so the earliest industrial revolution over 200 years ago, based upon steam-powered engines. Okay, and then electricity came along about 100 years later, and then of course the computer internet age, which we've all been part of, most of us, for the last several years. And now it's really different. It's a different thing. It's not just about computing and internet. It's about the hyperconnectivity between everything, all things. And what's connecting them is not just networks, but the flows of data and information that's shared to and from those things. Data that's produced by, informed by, driven by, the fuel for all these different technologies. So this 4th industrial revolution is truly changing work, future of work, careers, jobs, everything. So one thing that's interesting about this chart here is if we sort of think about sort of what's really changing in the workforce, the best sort of singular example that you can trace back 200 plus years of a profession, and that's farming. So at the beginning of the first industrial revolution in the 1780s, 90% of the US population workforce, 90% of the workforce were farmers. 90%. 100 years later, at the start of the electricity boom, the second industrial revolution, about 50% of the US population was farmers. At the start of the computer age, in the last 50 years or so, 5% of the US population was farmers, and now less than 0.5% of the US population workforce are farmers. Less than 0.5% of the population who are now feeding 10 times more people than they were 200 years ago are doing the job that was the dominant position 200 years ago. And so every industrial age brings a transformation not only of the technologies, but the work we do. So a really interesting stat came from the World Economic Forum, yes, WEF, World Economic Forum. They gave a few numbers about the changing workforce and some of the negative naysayers, and I'm a more of a positive spin person, the negative naysayers picked up one number in that report and said, wow, look at this. 75 million jobs will be lost as a result of AI and automation and these emerging technologies within the next 5 years. 75 million jobs will be lost. Isn't that terrible? But the very next sentence said 133 million new jobs will be created. And I can do arithmetic. That's 58 million new positions that need to be filled. Assuming we can translate the 75 million to those other positions, which is just something I'm working on in a project I'm calling Career Relevance, because data and coding give you both career relevance and job security. We heard in the earlier little video clip there, once you do that first line of code and see the results, you're addicted. Same thing with data science. I've done a lot of data science hackathons, and as soon as people see they can do stuff with those things called smartphones that are in their pockets already, every kid who entered my science class who declared to me they hated math and science became a lover of math and science after that class because they saw the power of what they can do. So we're really in this age, not just of an industrial revolution, but an innovation revolution, innovating new jobs, and innovation of new work, innovation of new opportunities, and many of these opportunities, like I said, 58 million new ones that we have to figure out how we're going to find the people to do that. So this internet thing has been around a while, and I like to tell people, well, the internet used to be a thing, so now with the Internet of Things, what I like to say is things are now the internet. Okay, everything is on the internet. Of course, in the very early days of internet, people remember those days? People put their coffee on the internet. Anybody remember that? Thank you for waving. Yes. People actually put their coffee, a webcam in their coffee room to see how much coffee was in the urn. Okay, but literally we're putting sensors on everything, so things are now the internet. And I like to say that the value of this is not even sort of the obvious value, which is all the data being produced by and used by all these things, but it's the context that those sensors give us about the world. Because all those data streams are coming from something that's taking place at a place and a time in a context at a location. So all this information gives you contextual knowledge about what's going on in that environment at that place where that sensor is. So literally, we're talking about the age of context now. Actually, there's a book on that right there on the screen. Okay, and another book I found recently, Outside Insight, how you can use these external data sources to even do better with all of the data you have. It's context everywhere, literally, to infinity and beyond. So who are we? So we're here today at Code One, in this beautiful place. We're digital technology professionals entrusted with this data. We're entrusted with these digital assets from our firms, our businesses, organizations, our clients, whomever we're working with. And our mission through all this simply is to discover and deliver value from these data assets. Because as this guy said, without data, you're just another person with an opinion, right? So this is how I set our mission, to discover and deliver value from data assets. It's a slightly shorter version of what Larry Ellison said yesterday. But I wrote my slides before he said this yesterday, so I think we're in sync here. He said that our mission, speaking of Oracle, our mission is to help people see data in new ways, discover insights, and unlock endless opportunities. So I'm here to talk about seeing your data in new ways and discover insights. And some of those new technologies, which I'll mention briefly, you'll see a bunch of them fly by in the remaining minutes here. Those will be chances for us to unlock these endless opportunities. So this is an eye chart. Don't try to read everything on that slide. But I just call this my expanding frontier of emerging technology. So if you could read all this, you would see things like AI, 5G, drones, robotics, deep learning, virtual assistants, machine learning, virtual reality, augmented reality, and on it goes, okay? All getting down towards the bottom, we get autonomous vehicles, quantum computing, computer vision, digital twins, blockchain. So we got this expanding frontier of new emerging technologies. Some have been around for a while, some yet to come, like quantum computing. But I like to say a lot of these things, probably, I wouldn't say necessarily 100%, but probably 99% of these things are inspired by data, informed by data. That is, it's the fuel that comes in. It's enabled by data, and it allows us to create value from data. So what do we do with all the data we're collecting, which is an enormous quantity? Our mission, again, is to create value from all of that. So value is achieved when you take that data and get something out of it, a decision, an action, a product, Okay, that's where you get value, not just holding the data. In the early days of the big data hype revolution, which is like almost 7 years ago now, maybe more than 7 years ago now, the start of the big data hype revolution, people would go to conferences and brag about how much big data they have. All right, and then I would get up and speak, and I would talk about this Excel spreadsheet that I had with 26 columns and a couple thousand rows. And they said, well, that's not big data. I said, yes, but there's 26 factorial ways that my students were investigating the relationships between those 3,000 galaxies and these 26 physical parameters. And if my students spent 1 second on each one of those 26 factorial combinations, evaluating it for principal components and clustering analysis and outliers and all kinds of things, if they spent 1 second per combination of those, it would take them 10 to the 9 lifetimes of the universe to analyze all of that data. So even a simple little spreadsheet can be big data. Okay? So it's not about volume, it's about the big value you can extract from it. So there's sort of 3 broad categories of discovery from data, that is data science and AI applications that we use data for. Image understanding, language understanding, and next best action understanding or decision making. And as you might see there, a lot of these words have sort of an anthropomorphic meaning to them. And not too surprisingly, because when we're training our AI, when we're collecting data, we are emulating exactly what the eyes, the ears, the brain, everything that we have is already doing. It's receiving sensory inputs from our world and making decisions about next best action, next best thing to do from that input. And that's what we're trying to achieve here, is that cognitive power in our autonomous systems that we already naturally have as human beings. So those 3 broad categories are how we bring data to action. So it's really about connecting the dots, all right? So data itself, just bunches of ones and zeros, but when we start seeing those relationships, so we start examining those combinations of the data where cool things happen. Okay, so people who bought that book also like this book. People who watched that movie also like this movie. We know about recommender engines. It's about connecting the dots in that space of data to make decisions and take actions and deliver value. Okay, so there's a very large company out there in the world, one of the largest companies in the world, who has recommender engines. You probably know them by a name. That particular company, nearly $1 trillion business. A full 30% from what I've been reading, full 30% of the revenue of that $1 trillion business is from their recommender engine. Think about that for a second. 30% of the revenue of $1 trillion business comes from a machine learning algorithm. Yeah, wow. I can read your lips. That's taking data to insights to action. Okay, so AI to me is not artificial intelligence, and I have a slide about this later on. There's nothing artificial about it. It's really augmented intelligence, accelerated intelligence, actionable intelligence. It's all these things that give us value from our data. So really what I'm saying is about look at the connectivity. And remember, again, the 4th industrial revolution is about that hyper-connectivity. The connectivity, not only in our data sets, but even among the technologies. And that's really what I'm looking at today, is that when we start bringing together 5G and AI and IoT and autonomous vehicles and digital twins and blockchain and whatever, we start bringing these things together, we start building new and interesting products that no one ever imagined before. And if there was 26 things on my list of emerging technologies earlier, and I think there was about 26, there's 26 factorial ways to combine them. And if you spend 1 second combining each one of those and create a product for your company, you'll have a new product every second for the next 10 to the 9 lifetimes of the universe. So get busy, folks. Okay. But Leonardo da Vinci said it best several centuries ago. He said, learn how to see, because how we see is we not just see tunnel vision, we see the context around it. Okay, we realize that everything is connected to everything else. And so it's starting to find the connections between those technologies and those data sets and all those different combinations that will start delivering the value in newer and more innovative ways than ever before. So yeah, autonomous vehicles are great, blockchain is great, 5G is great, all kinds of things are great, augmented reality, virtual reality, drones, you name it, all kinds of cool things. But imagine that you start combining those things in different ways, what kind of products you can generate. So the number of combinations and interactions in this graph is really big. As the little intelligent student says there, how big? Very big. It's a combinatorial explosion. So people talk about the exponential growth of stuff. Well, I got 3 curves on this, what I call my holy shoot graph. I think you read the axis there. It's my holy shoot graph. There's a linear growth curve, which is like 2 times x. There's an exponential growth curve, which is like 2 to the x power. And there's a combinatorial growth curve, which is like x to the x. That's quite a bit faster than the other ones. So when people say things are growing exponentially, said, Dad, that slowly? That's pretty slow, actually. Combinatorial growth is blowing away everything. All right. So what kind of things are we talking about here? Okay, let's cut to the chase here. Okay, I put discovery from data, that is data science, in sort of 4 broad categories. I mean, it doesn't capture everything, but sort of the 4 broad categories. So we got class discovery, that is discovering the segments, the clusters in the population, subpopulation, subsegments. Okay, so that diagram in the upper left, where you see data clouds DC 1, 2, and 3, data clusters 1, 2, and 3, in a 3-dimensional parameter space, P1, P2, P3. That's just made-up synthetic data just to illustrate clusters. So we got 3 clusters, dominant clusters in there, and there we see a few more. All right, so in class discovery, not only discovered the dominant classes, but we just start discovering as we add more data, the value of adding more data here, we start seeing other clusters emerge, other segments in our population. So these might be populations of clusters. They may be segments of behavior of a machine. They may be segments of the pathway of a medical diagnosis or a drug treatment. Okay, so all these clusters are segments of some population. And as you add more data, you start discovering more of those segments. But the most interesting thing about this, what you discover here also to me is you learn the boundaries that separate them. All right, what makes Data Cloud 2 different from Data Cloud 3? So if Data Cloud 2 is a certain diagnosis for a disease given a set of diagnostic measurements, P1, P2, P3, if you have been diagnosed with diagnosis 2, and your lab results put you right near the boundary of Data Cloud 2 and Data Cloud 3, that is diagnosis 2 and diagnosis 3, if your lab results put you real close to that boundary, you know you have a very strong chance of a false positive or a false negative, because you're very close to a boundary to a new class. But if you're smack dab in the middle of Data Cloud 1, that is diagnosis 1, you can probably be fairly certain that's what it is. Okay, so learning not only the segments of the population, but what distinguishes them is the real beautiful power of all this data. So class discovery is one thing. And oh, by the way, my astronomy friends like to call this the banana diagram, because Data Cloud 2 looks like a banana. All right, but I just like to call it the peanut, banana, and potato diagram personally. Anyway, so the second thing we can do with our data is correlation discovery. All right, so that's sometimes called predictive power discovery. When you see X correlates with Y, okay, then X becomes a surrogate for Y. So given X, we can figure out what Y will be. Okay, that's predictive analytics. That's predictive power discovery. But as we add more dimensions beyond X and Y, so X and Y are 2 dimensions, if we start adding more dimensions, you start getting insights. Well, that's good. We have a 3-dimensional plot here, so I got more than 2 dimensions. Good. Okay. So the 3rd dimension starts giving you insight. That is, we see this Data Cloud 2, for example. It has a certain slope in that correlation in Data Cloud 2 between parameters 1 and 3. And that slope, that correlation, strengthens at a certain place. It's a weak correlation, then it becomes a stronger correlation at some point later on. Well, if you just have parameters 1 and 3, and you just see that it changes at a certain point, you really don't have any sort of causal information. You don't have any contextual information. Remember the internet context, remember? We don't have any contextual information as to why it's happening at that point, in that elbow. Why is it changing there? I can tell you that it is changing there. I can build a predictive model and say it'll change there, but I don't understand why. But if we start looking at our other data sources, hopefully other data sources will give us some contextual information and maybe even some causal information. For example, P2 might be a variable, a feature in your data set over which you have some control. Okay, it might be a marketing campaign, a discount on a product. It might be the temperature setting on an engine. It might be something you have control over. So even though you might predict a certain thing is going to change, if you can adjust that parameter, you know that you can move the P3 response function in any direction you want, further down or further up. That now becomes prescriptive power discovery. So correlation analysis can lead to causality discovery if you have multiple dimensions, some of which are causal variables, that is, conditions under which you have some control. So predictive maintenance on engines, for example, is a great example of applying AI and machine learning to manufacturing or machines or jet aircraft engines or whatever, which it's nice to know since I'm flying home this evening. They do these predictive maintenance on the engines. And if you predict that the engine is going to fail at 2 o'clock tomorrow morning en route from San Francisco to Baltimore, I'm going to be kind of unhappy that they didn't take that plane out of service. Okay, so just like if your doctor says, well, I diagnosed you with cancer and you're going to die tomorrow, have a nice day, I'll send you my bill, well, you're going to say, wait a minute, can't you do something, doctor? Can't you do something? Oh, yeah, I can give you a prescription. So prescriptive maintenance, prescriptive analytics, prescriptions are about doing that thing that you know based upon your data, clinical studies in the case of medicine, but in the case of our data systems, finding those contextual causal variables. What can I do to change the outcome? I want a better outcome. I want a different outcome. So predictive modeling says, given X, find Y. Okay, I see a correlation of X versus Y. Given an X, I can tell you why. Prescriptive analytics is the exact opposite. Given Y, find X. Here's what I want it to be. What can I do to get it there? Or I don't want it up there, I want it down here. Depending upon I want something, that variable to have a different outcome, what do I need to do to change in my causal contextual environment to produce the outcome I want? That's a prescription. Okay, so again, predictive analytics, given X, find Y. Prescriptive analytics, given Y, find X. Now, I've had a few decades of mathematics, several semesters of calculus to get to a physics degree. You don't need all that to realize that given X, find Y, and given Y, find X are really sort of opposite mathematical statements, okay? They really are opposite things. But they all derive from finding those correlations in your data, especially when you have the higher dimensions. And so what you're really discovering is how that system behaves under different circumstances. How does it evolve? How does it respond? What does it look like? That's called the object's DNA. So all that data is giving you the object's DNA. Okay, so that's 2. Number 3 is outlier detection. It sort of speaks for itself, except it doesn't, because my friend who put together this banana diagram did something really clever. Can you see from your seat in the middle of Data Cloud 2, the lower section of Data Cloud 2, there's a little blue-shaped, sort of heart-shaped thing there? Can you see that? The lower port of Data Cloud 2, there's a little blue smudge there, sort of heart-shaped, kidney-shaped. That was intentional. That's not a smudge on the screen. That was intentional. That's meant to represent a void. It's a region that the data avoids that region. Now, in astronomy, we have lots of examples like that. And when we find those things, it tells us there's some physical law, there's some astrophysical reason why that thing in nature doesn't want to be in that spot. And so when you discover those voids, it's an aha moment. It's a discovery moment. It says, what is it about the system that's telling me that it can never be there? Okay, so an outlier can sometimes be right smack dab in the middle of your data set, and yet it shouldn't be there. That's an inlier. And it's just as interesting and surprising and anomalous and novel as the outlier who's sitting 7 standard deviations from the mean. So an inlier can be 0 standard deviations from the mean and still be extremely interesting discovery. So surprise discovery, number 3. And then when we get to number 4 here, it's the 4th one deserves its own little cartoon of its own down at the bottom left there, and that's link discovery, network analysis. Okay, discovering interesting associations in links, just like the product recommender engines, or even like marketing attribution, or fraud detection, because it's not A communicates to C, but A communicates to C through B. Okay, so marketing attribution is just like that. Illicit money transfers is just like that. It goes A to B, B to C, because if it was A to C, someone would notice and they would get arrested. Okay, so it's the hops in the graph and the dots that are not connected directly, but transitively through other nodes in the graph. That's where the real discovery happens. So associated and link discovery is another great way of discovering value in your data. Okay, so all those different ways of discovery can be applied at different levels of analytics maturity. Okay, so these levels listed here are, in a sense, orthogonal to the things on the previous slide. That is, you can do all the things on the previous slide in some way or another at each of these different levels here. So there are different ways of describing what we're doing. So the analytics are the outputs, the outcomes, the delivered value from all the stuff we're doing, all the data science we're doing, all the discovery we're doing from our data. So what are some of those things? Well, number 1 is descriptive analytics. You can produce a report and say what happened. All right, now that may seem kind of boring because it's a historical hindsight what happened type of thing. But if you're in a publicly traded company, which I am and Oracle is, you know you have to do quarterly business reports for Wall Street. It's required by law. So descriptive reports are invaluable and keep you out of jail. Okay? So even though it might be at the lowest rung in this maturity ladder, it's still absolutely essential in some settings. So what you're doing in descriptive analytics is you're answering the prescribed questions. You're answering the questions given to you. You'll see when we get to number 5 here, I'll sort of jump to the gun here. Number 1, you're answering the prescribed questions. And number 5, in cognitive analytics, you're discovering the questions you should be asking. That's the fully human cognitive role or analogy for analytics, which is you look at your data and say, why is that happening? Why is that outlier there? Why is there this void here? Why is this trend suddenly changing slope? Why did this change under this condition, but it didn't change there? What is this new emerging subcluster in my medical data or in my customer data? All those questions, don't avoid them. Embrace them. And sometimes the question may come from the most junior person on your staff, and it may even come from a family member because you're preparing your presentation for the Oracle Code 1 stage, and you show it to your family before you leave home, and this youngest member of the family who's 6 years old said, "What's that?" My grandkids call me Poppy. "What's that, Poppy?" Well, that didn't actually happen, but it did happen years ago when my kids were that age. Okay, so let anybody look at your data, because they will see things that maybe you didn't see. So cognitive analytics is that highest level. Now find me the questions you should be asking from your data. But along the way, we're doing these things, and I give them these funny words: hindsight, oversight, foresight, insight, and then finally I had to come up with something that rhymes with sight, so right sight. Okay. So hindsight, that's descriptive. Diagnostics is oversight. That's sort of real-time analytics, what's happening right now. Predictive analytics, we already talked about what will happen. That's foresight, sort of seeing the future. Forecasting. Prescriptive analytics, that comes from the insight we talked about. Given all these other data sources and these other dimensions of the data, we have insight into how our system behaves in ways we never saw before because we have all this contextual data now. So insight discovery enables us to prescribe better outcomes, how to optimize outcomes, choose the next best action, make the next best decision given our data. So that's prescriptive analytics. And then cognitive analytics is, again, having that full view of things where you say, what is it that I should be doing? What is the question I should be asking? What is the right thing to do right now in this context at this point? So cognitive analytics moves beyond just answering the given questions, but just generating new questions from your data. So those are the things we do with our data. So we produce value by applying algorithms to data, discovering patterns, and building models from them. So that's taking us through machine learning and data science, actionalizing it, which might be the AI, and then the products of those things are the analytics. So all that terminology is defined here on the screen. There's a couple of things besides the busy definitions there that I want to call your attention to. First, the very top 2 lines of the slide, it says, learning is an iterative process, right? You learn fast, fail fast to learn fast, we know that, right? The best way to learn something is to make mistakes and learn from it, learn from your mistakes. So learning is an iterative process. Science is an iterative process. So scientists develop hypotheses, they test them, and they do experiments to test them, and sometimes it doesn't work so well, so you refine the hypothesis and you try again. So it's an iterative process. So if learning and science are both iterative processes, it's not too surprising that machine learning and data science ought to be iterative processes also. So machine learning are these algorithms that learn through that process of failing, that learns from experience, just like a child learns from experience, right? So the best line I ever heard that describes machine learning also applies to raising teenagers, right? Good judgment comes from experience, and experience comes from bad judgment. So when you build a model, you build a rough model, and of course it's going to be wrong. And we have things like gradient descent and backpropagation and all these cool techniques in machine learning that feed the error information back to the model to adjust it to make it better. It's algorithms that learn from experience. Just mathematics is all it is. Data mining is how we apply that to data to do discovery. AI is how we apply that data to taking actions. Data science, then, is the scientific methodology that we apply to do all that. All the different pieces of science, hypothesis generation, experimentation, data collection, validation, refinement, all those things. That's the process, that's the methodology where we use the math build models that we test to deploy, and then when we deploy it, we actually then have the analytics. That's a deployed thing. And so the second quote I wanted to draw your attention to, besides all the definitions in the top line, was the thing in the yellow box on the right. That is the two most important things in data science. So if you remember anything else today before you leave and after you leave, the two most important things in data science are the data and the science. Because the data are the raw objective truth, the raw objective reality, the fuel for our models, and science is the methodology by which we hopefully don't trap ourselves into confirmation bias. Oh, that model worked. Test it, verify it, put it through some paces, try it on a different data set, see if it generalizes. Don't get stuck in a bias trap. It's an iterative process, and it's okay to be wrong first. Okay, so Thomas Edison, someone complained to Thomas Edison, that he failed 1,000 times to invent the light bulb. And he said, I didn't fail 1,000 times. I learned 1,000 ways not to build a light bulb. Okay, so failing fast to learn fast is an adoptable good practice in business. So analytics by design basically goes back to my last point at the very bottom of that last slide, which is analytics are the products. We need to focus on our business outcomes, our goals, our objectives. What is your mission? What is your North Star of your business? That should be determining what you do, where you go, and how you go there. All right, some people say they're data-first organizations. I'm not going to complain if that's a way you want to describe it, but I don't like using that phrase because every organization has data now. That doesn't distinguish you from anybody. Just like years ago, people would brag about how big their data sets were. And that doesn't separate you, make you distinguishable in the marketplace. What distinguishes you are your output, your products, the delivered value from your data. That's the analytics. So focus on what it is we want to accomplish, what are our business questions, and that's a good science practice too. Good science starts with asking a question, a hypothesis. What am I looking for? An hypothesis that explains this thing that I see. Okay, test it, verify it, go through a process. So analytics first is good business strategy. It focuses on outcomes which matter, and also it focuses on products, which are the value that we create from our data. And as you build products that are increasingly successful, and it may start with some very, very small things like a very simple recommender engine or a very simple chatbot that very simply is plugged into your customer service call center and answers the FAQs for people. Because like 80% of the questions that people call for call centers are just in the FAQs, which are already posted on your website. But people don't read anymore, so they call the call center. Call center people are frustrated because it's the same old questions, and it's right there on the website, people. So you can actually have an API, call a chatbot, feed it your FAQs, and you're done. No coding, no work involved, basically. And you've just solved 80% of your customer service calls. But not only that, you've made your employees really happy. Because the last thing an employee likes to do is answer the same question over and over and over and over and over again. So you're improving employee experience, which therefore translates into better customer experience. Happy employee, happy customer. You see the equation there, right? Okay, so by focusing on those small victories, then you encourage the culture to accept larger projects around AI and machine learning. Because there's a lot of fear in the marketplace and in businesses and companies and organizations everywhere. People fear job loss. But at every tier of the organization, people think, someone's going to do my work, or someone's going to do my decision making, or someone's going to run the company. So everyone thinks that they're not going to have a place anymore. And that's true. The jobs will change, but we'll need more people for the new jobs. So let's deliver value, and that'll inspire the culture change that'll lead us to those bigger implementations. So at the end of the day, this analytics by design means think about the products we want to deliver that are going to deliver the value, and there's some there at the bottom of the slide there. I ran out of room. I got the ... there because I put the word models in my original slide about 7 times in this place, because the models really, to me, are the key thing. It's the models of how customers behave, how your systems behave, how your website behaves, how your database behaves, how anything behaves, right? So those models become sort of the fuel, the engine that is driven by the fuel, which is the data, which leads to the output, which are the analytic products. So what's going on in that engine? What's going on in this machine learning engine? We talked about algorithms that learn from experience. Okay, that sounds pretty damn vague, really. What does that mean? Well, again, they learn from patterns and data what something will do or how something will behave. So just like I always say, like the first caveman comes out of the cave and they see this animal in front of them, they have to, first of all, they have to do object recognition. They recognize it's an animal and not a bush, okay? Okay, so there's object recognition, okay? So pattern recognition, or pattern detection, I should say, pattern detection. Then they do recognition. They have to recognize, is this something going to eat me for lunch or can I eat it for lunch? So either way, if you make the wrong decision, your day's over. Okay, your life's over. Okay, so it's clear that we need to learn from experience. And so supervised learning is given the training data, given past data, labeled data, how can we get an algorithm that can detect, for example, a cancer or a failing engine or a cancer patient or an unhappy customer or whatever. Okay, so we learn from feedback, from labeled data, from prior experience, historical data, training data, and build the model so we can deliver a better outcome, and that's called supervised learning. It's given past experience, we know how to deliver better. Then there's this thing called unsupervised learning, where you basically say, what patterns do I see in the data, independent of what my biases might be about what I'm looking for? Okay, so I might see these new clusters emerging, these new patterns emerging, these new trends, these outliers, these inliers, these new links in the graph, the social graph, the product graph, the knowledge graph. All right, it's unsupervised, it's data-driven. Okay, it's finding things in the data in a sense that the 6-year-old can find. All right, what's that? Why is this? All right, asking those questions, finding that hidden structure that you didn't previously know about, unsupervised learning. So it doesn't necessarily require labels, okay? So you're looking at a radiological image to see if a patient has cancer and there's some funny little smudge over here on the lung. Well, would you like for your doctor to ignore that and say, okay, you don't have cancer, bye. You should have paid attention to this thing over here, okay? Because that might be something serious. Okay, so the third kind of machine learning is reinforcement learning, and that's how the machines learn how to play chess and Go and beat the world champions. Okay, they play the game with a reward stated. What's the reward? You know, what's this, how well am I doing? There's a score, there's feedback, and that reward process trains the machine how to do better. It says, okay, if I do this, I get worse, or if I do that, I get better. So that reinforcement learning is a very significant iterative process. Okay, and that's really powerful for decision-making in autonomous systems because it's learning rapidly, from its experience. So traditional programming, this is oversimplification. Don't get in an argument with me about this because it's not my slide, but I actually do believe this slide. So traditional programming, right, is you write a program and you give it some input and it generates an output. That's sort of what I did back in my high school days. I had these positions of the planets on the sky. I put it in a program and I could generate those numbers. I was amazed I could generate the predicted positions of the moons and the planets just from what I was doing right there. Traditional programming like that. So supervised machine learning, I'm going to emphasize supervised because that's what specifically in this case. We have the data, we have the input data, we have the labels, that is, these images represent patients who have cancer, these images represents patients who don't, or this time series represents an engine that has normal behavior, this represents an engine that has a malfunction that's about to happen or will happen soon. This data predicts happy customer, this data predicts unhappy customer. Think about sentiment analysis, right? So we have data and we have output. We know what the outcome will be. Then we find the model, we find the program that reproduces the data in the output. Okay, so what we're looking for is the program, the model that will generate from the input the desired output. Then we apply that to our new data. Okay, so the top level of this plot where you see the blue arrows, we have training data coming in. We extract interesting features from the data to generate a model, an algorithm from machine learning, whether it's class discovery, correlation discovery, novelty discovery, link discovery, whichever we're doing, and we build a model that can produce correctly those outputs. We correctly label a cancer image, correctly label an unhappy customer, correctly label an engine that's malfunctioning. Then, once you have that output, again, the output is the program, then you can apply that program to new data. So then, you get sort of to the more traditional input, program, output. Okay, you feed the new data through the model and generate the output. That is, you predict the class variable, cancer, no cancer, engine fail, not fail, happy customer, unhappy, whatever. All right, so you apply the model, that's where the green arrows are. But remember this famous quote from the statistician that all models are wrong, but some are useful. So don't get stuck with analysis paralysis saying, well, this is not entirely correct. Remember the 80-20 rule, right? I mean, 80% of the value comes from the first 20% of effort. Okay, so you can get that 80% of value in your first 20% of effort. Sometimes you don't need to spend all that extra effort, 5 times more effort, just to get the last 20%. All right, all models are wrong, but some are useful. Sometimes the simplest models are the best, and I can tell stories about those, which I don't have time to do today. Anyway, so in this rapidly expanding frontier, there's some examples which follow. There's a link to the slides at the end where you can read all these things in gory detail. I don't have the time this afternoon to read through all these for you. But machine learning, okay, so there's like 9 or 10 things from that previous slide that I'm going to just fly through here. So machine learning algorithms that learn from experience, for example, recommender engines, digit detection at the post office so it can read the zip code on your letters, spam email detection, cancer detection. I talked about those. So these are algorithms that are trained from historical data to learn how to label things correctly, models that learn how to get things right. So AI, that actionable intelligence, that accelerated, augmented, assisted intelligence, augmenting the human in the loop, nothing artificial about that, bringing data to action, those applications. Well, the first 4 are the ones that were just on the previous slide. The algorithms and models that we learn, that's just mathematics and coding. Now we apply it, that's the AI. So those first 4, 1 through 4, my examples, as it says there, examples 1 through 4 are the applications you just saw. Other examples include credit card fraud alert and conversational AIs, the Siri, Alexa, chatbots, and so on. Robotics, we know about that. Okay, so robots respond to sensory inputs to move through their environments. That's a data input, decision output, action output, based upon data. 3D printing. Now this may seem kind of boring because 3D printing, you sort of have to build a model of the thing, and then you feed the model into the printer and it prints it out. That's called additive manufacturing. It may not seem too interesting, but 4D printing is really the wave that's coming, where the system can, for example, using carbon nanotubes, it can actually respond to sensory input and change shape in real time. So medical doctors are using carbon nanotube heart stents that they implant into patients with a sensor, a heart monitor, blood pressure, and various sensors in the body. And when that patient is going through some stressful moment or has a sudden heart fibrillation or higher blood pressure or body temperature change or something, the shape of the heart stent will change in real time in their body in response to those sensory inputs. That's 4D printing. It's changing in space and time in response to input data in the body without further surgery. That's insane. There's a YouTube, you can read about this. All right, virtual reality. Again, it's a virtual environment, but a lot of times there's sensory inputs and sensory motions that make the reality experience real because it's actually detecting all that from sensors. Augmented reality is when you now have data superimposed on the real world. So whether you're in the shopping mall and you say, where are the sales? or I go into the grocery store, where are the Cheerios? Okay, so I could have that augmented reality right there on my phone. So it shows me my store with labels on it. Or it might be in disaster response, showing where there's down power lines or patients or people in most distress, okay? Or other kinds of things. Or there's augmented reality of this app where you actually can stand in front of a mirror in a store, try on a new outfit without trying it on. Stay in your own clothes, select the clothes you want to see how you look in it, and it just shows you in the mirror with those clothes on without you actually having changed anything. Okay, pretty amazing. Okay, IoT, I already talked about that. It's data everywhere, generating fuel from these sensors to all kinds of things. Autonomous vehicles, we don't need to talk about that at length. We know about that. Obviously, sensory inputs, driving actions, literally. Drones, similar sort of thing. Sensory detection, whether it's for disaster response, military applications, or construction sites, or just for fun, or whatever, sensory data analyzed by algorithms to say what's going on. All these things are examples of dynamic, data-driven application systems, okay? So all these things are doing measurement from sensors of all kinds. It's doing inference, that is building a model of how I think this thing is behaving, building a prediction to say, if I do this, this will happen, or this is likely to happen. So it's both predictive and prescriptive, actually. And then the last part is this S called the steering. That is the actual action taking. An autonomous system who now takes an action based upon this chain of events. I measure something from sensors everywhere. I infer something from it. I make a decision. Okay, so decision is really a prescriptive analytic process. If I decide to do this, this might happen. If I decide to do that, that might happen. That's what happens in boardrooms every day. It's a prescriptive discussion. If we do this, what will happen? If we do that, what will happen? So you go through that process, that inference from your data, data-driven. That's why this slide is about dynamic, data-driven systems. Then you can have an autonomous system anywhere in the world, including in your database. Which brings us to the autonomous database at Oracle. But I talked to NASA folks for years, long before anyone had a vision of autonomous databases, of how can we use AI, or how can we use data science for data science? Using data science to label data. Use AI to create tags, semantics, taxonomies, descriptions, indices, organizations of our data. Imagine a library. Imagine walking into a library. People remember what libraries were? Yeah, sort of. Mostly people with gray hair. Anyway, so you go to a library. The books are organized alphabetically by the third letter of their middle name, right? No, they're organized by the Dewey Decimal System, so you know how to find something. There's a system. They're indexed in a certain way. But imagine if you walked in that library and the index suddenly changed based upon your preferences and your interests and the things that you like. And suddenly it's all organized according to your personal preference, your personal interests. Suppose I like cooking in the mountains, so I want some outdoors books next to some cooking books. But I want to do it under the stars. I'm an astronomer, so I want it next to the astronomy books. Okay, so the whole system organizes the data and presents it to me based upon my digital breadcrumbs, things that I have already done with data. How have I used the data? How have I found interesting things in the data? Even digital breadcrumbs that can identify friction points where the person constantly keeps trying and then doesn't have success. You can detect that in the data. So adding data to data, using data science for data science to make our data systems more useful for the data applications we've talked about. So truly, it's a data world after all. Data really helps our world go around. And let's not forget what Larry Ellison said, that our mission is to help people see data in new ways, discover insights, and unlock these endless possibilities. So thank you very much. Come for the data, stay for the science.
All right, that was great. So we're going to talk a little bit now about how you start to take some of these concepts around data science and machine learning and turn them into applications. Okay? So right now we've got this phenomenon really where there's been an explosion of technologies for developers. There's languages, there's frameworks, there's platforms. In some ways, it's really fueled the availability for developers to be more productive than ever. Some of this is being built by developers themselves via open source. But the ability to solve problems quickly and correctly has moved up exponentially over the years. And why is this, right? So in a sense, it's always been easy for developers to cut code. And technology is something you can learn, right, and apply. I think what's changed now is that there's a possibility of architecting a new generation of end-to-end solutions very quickly. You can prototype them in real time. You can upgrade these projects toward production very quickly. And one of the major factors that has opened this up is really the emergence of reliable and stable public cloud platforms, right? You don't have to go to data centers and rack and stack machines. Your compute, your storage, your data management, it's there, it's available on demand. So now you can get to where you have complex solutions and the infrastructure to run them really within minutes, right? So that means the barrier to adopting new technology has gone down quite a bit. The cloud's now opening up a new paradigm, a new type of application as well. And we're going to talk about that today and tie it back into some of these topics around data science and machine learning, right? So we see this emergence of what we're calling an intelligent cloud native application. And we mean intelligent because it typically involves the embedding of machine learning models directly within the applications themselves. And this has a lot of implications for how to think about apps. For one thing, it means that data takes on a new kind of centrality, and developers have to start thinking differently about data and about data management. right? So applications are no longer about CRUD operations over top of a database. There's different scale of data management, different kinds of data management systems. And more importantly, when you have machine learning models, you have to think about the data differently. In many cases, the knowledge is embedded inside the data, but even the developers themselves that are utilizing the model may not really understand fully what that knowledge is. So we'll try and unpack that a little bit here. But to do it right and to make it maintainable, and to ensure that the machine learning models stay correct, stay consistent as data itself starts to change and drive appropriate decisions over time, applications really need to be cloud native, and we'll try to show you why today. So let's talk a little bit about modern applications and the evolution around application development that's gone on over the years, right? A lot of times now we talk about apps, we talk about services being born in the cloud. And this is the end of a long process. So way back in the 80s, going into the mid-90s, data centers were built with physical servers, apps were very monolithic, the way teams work was very much the traditional waterfall style. As we move forward in time and we get into the late 90s, in the early 2000s, a lot started to change, right? Here we had the emergence of virtualization. Right? You saw probably some of the announcements around VMware on Oracle Cloud today. A lot of virtualization technologies opened up and made things more flexible. We also had N-tier applications. This was the heyday of the application server, the JEE standards and so forth. So people started to think about applications being very much multi-tier and not monoliths. Data centers were starting to provide hosting and converting over to using Linux servers, commodity hardware. So the cost overall of deployments was going down. And then we had the emergence of agile methodologies, right? And this was back, if you look at this period when extreme programming books were out, they were almost like, I remember going through each of these books in the extreme programming series, and they were almost like religious texts at the time, because it was so different than the way people had thought about waterfall applications. So, so somebody else remembers too. So then we get to today, okay? And this evolution continues to change, but it's building on these foundations, right? So now we're seeing containers replacing virtualization, easy to have, very fast and agile deployments. Apps are often designed as loosely coupled microservices, and DevOps has become very much a standard thing. Continuous integration, continuous deployment. It's very much the way of the world these days. So this move to cloud-native applications has been really about fast and reliable application development. And it sits on this lineage, and it's been proving itself out to be very effective. So when you go and you think about how you build a modern app, right, the agility is one of the key factors. The ability for deployments, for operations, and for the evolution of the application itself to move quickly, and move reliably, move correctly. So typical workflow, let's just kind of walk through this image a little bit. Teams, they're going to write code. They're not necessarily bound to a particular tool or particular development language. Teams can select the DevOps environment that they want to set up their development pipelines around. Once you get the code built, compiled, you can package it up, put the libraries and binaries together into a container. So now you have this unit that's executable, it's very portable, it's very fast for deployment. Push the image into a container registry, and you're ready to go. You can use Kubernetes, popular open source framework, to stage the containers into a cluster, and you can start to run your application or your microservices. So oftentimes you'll have a series of microservices that are bootstrapped, where each container is kind of serving a specific set of functions within the overall application. You can spin them up and down very quickly, especially compared to a virtual machine or traditional binaries thrown onto an OS on bare metal, right? So each microservice tends to be independent of the others. You have more flexibility, but you have more resilience within the application architecture overall. When it's time to upgrade a microservice, or when you're doing bug fixes and patches, it's typically replaced directly, right? No more patching systems. You're really making changes in place, just replacing containers, moving forward with your testing, and upgrading your application in real time. So each of these things Each of these microservices themselves may be responsible for managing data, right? That's typically, often at least, in a database. It can get challenging when there's a lot of different microservices together and a lot of different databases, and you're trying to get these things to work collaboratively and not have bottlenecks. So one of our speakers, Maria, who will be coming up, will talk to that a little bit. But this model requires, it's effective, it works, it's flexible, it makes it easier to have rapid progress, rapid evolution. It also has an overhead from an operational perspective, because now you've got lots of little services, lots of little servers running. And I think cloud platforms are getting smarter about this as well. So this is where we're starting to see the emergence of models where you can take the container and deploy it into a serverless architecture. So you can get the best of the design characteristics of the microservice model on the one hand. On the other hand, we can reduce or eliminate the complexity of operating the system. So the idea with a serverless model, something like what we offer in Oracle Cloud Infrastructure, our function service, which is based on the open source FN project, the idea here is that when a request comes in for the service, the code is instantiated, it executes, it completes the work, and then it can shut down. So you're really only paying for what you're using, and you're not really responsible for running the back-end infrastructure. That falls on the cloud vendor. So it's a kind of a cool way that the cloud platforms are getting smarter about helping modern applications move fast. Now, that touches on maybe some of the typical approaches to designing a macro architecture for an application. But what about this idea of intelligence, right? Here we see that there's a new breed of modern applications that's emerged, and they're using machine learning to drive the decisions within the app itself. And what's cool about this is that oftentimes you're moving away from static rule-based systems, you're getting better outcomes, and you're really able to drive business decisions that are derived directly from the data that the business has, right? So a lot of this today is very real, right? It's emerged as a pattern we're seeing now repeatedly, almost typically, as we're talking across projects with development teams, many different kinds of enterprises. I have a few examples here. So one that I like quite a bit is medical diagnosis. I did a general session yesterday on AI and artificial intelligence where we demoed an application where you fed it x-rays, chest x-rays, and the system learned to identify pneumonia. Now, what's cool about this kind of system, and Dr. Bourne had talked about cancer identification, is that oftentimes the machine learning models can do a better job than radiologists, a better job than humans, right? So that doesn't necessarily mean the humans don't have a role, or you don't want humans checkpointing things, but there's a lot of power in this. Another neat example, smart agriculture. We've got guests here at AgroScout, which is an Israeli startup. Here at Code One, they're doing a session. They've developed an application where they have low-cost commercial drones that generate images of crop structures, and they can detect pest infestations, they can detect diseases all the way down to the level of individual plants. And it's much more cost-effective than doing it with satellites or trying to do it with airplanes. So it's a really cool example of a high-value AI-driven application that in some ways impacts us all, right? We're all consumers of agricultural products. Oracle itself, internally, our SaaS applications, we're using machine learning all over the place. So in Oracle Cloud, we have an offering called the Oracle HCM Cloud, and it uses machine learning models to sift through resumes and match them with best fit job openings, right? There are machine learning models that are used to help customize career progression for employees within the application environment. Similarly, within the Oracle Customer Experience Cloud, we use machine learning to recommend best offers for salespeople, right? Finding not only what is the fit for the product from the data we have about the customer, or the data that you have about the customer, but also how do you optimize around the pricing that is going to make you get a deal where it's a fair exchange of value on both sides, right? So these are great examples of how machine learning is already showing up in custom applications, in commercial applications. So the question really is, how does this impact your app? How do you go about doing it, right? And it's an interesting problem because the centrality of data and the importance of having a cloud platform really become clear when you look at the full life cycle of a machine learning model. what happens when you're going to engage application developers and data scientists together to create solutions based on artificial intelligence. So first, data scientists have to be able to find the data, explore it, understand it, right? Key thing, actually, for a lot of organizations, just getting the data is a challenge. Once they have the data, they got to be able to work with it. And one of the main tasks in a data scientist's life is what's called feature engineering. And this is where you're selecting the right data sets, you're working to scale it, you're forming the data, you're combining it, limiting to subsets, et cetera, in such a way that it's optimized for feeding into the algorithms that are going to be used to build the machine learning models. So feature engineering's key task, turns out it's hard, right? Because you want to get an optimal model, and it's sensitive to the kinds of data and to the tuning of the model, et cetera. On a data science platform, like what we have in Oracle Cloud, we actually use machine learning to help make those tasks easier. We automate a bunch of the feature engineering work, and we call this AutoML characteristic of the platform. And now, once you get the model, you start to figure out what your data sets are, and you start to optimize the data for the models. You have to do the training. It's not a one-time event, right? Training often requires specialized hardware. You want that hardware to be available on demand. We've seen a number of examples where there are very large data sets, and users are training models with CPUs. It's taken them weeks and weeks to produce a model. They've switched over to GPUs, which are much more efficient. They're built to do matrix math, and they're able to build the same model in hours, right? GPUs are expensive, so having a platform where these are available on demand, where you can get these workloads processed and turned around quickly, is another key part of a platform that you want to have available. So third, the next area, once you've built a model, they need to be easily deployed. And it turns out this is another surprisingly difficult problem as well. Lots of times organizations are struggling where they're trying to get the model that data scientists have created on their platform into production. They're bringing in engineers. They're trying to re-implement the algorithms, re-implement the models. It's tedious. It's error-prone. It leaves aside security and governance concerns. So you want a platform that takes all this into account. It makes it easy to operationalize the model so it can be embedded inside the application. That's an important step, obviously. But once you have the model is only as good as the data. And invariably, data changes over time. So think about this. If you built a predictive model for a stock market investment, and you built that model in 2006 or 2007, we had the real estate market debt crisis in 2008. If you were using the model after the crisis, it's going to give you very bad results, right? It's going to be basically useless. So you have to have a platform beneath the application that's making sure that the models remain predictive, that the predictions are effective, that as the data changes and the predictive efficacy of the model declines, you can retrain the model, you can redeploy the model, and you can automate this process. So the best part, in our opinion, the best place to do this by far is a cloud platform that's designed to manage machine learning models, right? So that's an important part of the modern data architecture, the substrate for machine learning that underlies or is a companion to the modern application architectures that have emerged over the years. So we at Oracle, what I'm going to show you here is a kind of a snapshot in the large of Oracle's second generation cloud infrastructure, OCI. Okay, it provides bare metal compute, virtualization, and containerized compute. Importantly, it's got things like GPUs on demand for performance-intensive workloads like machine learning. Right? So the platform is built from the ground up to do HPC and data science type workloads at that basic infrastructure level. We also have a whole array of services for developers to use to build these modern applications. You have a choice of programming languages and frameworks. You can use Java, JavaScript, Node.js, Python, Ruby, et cetera. You're not locked into any platform in particular. We have tools for developers and DevOps. We have free tools like Developer Cloud, but you can use whatever you're already familiar with and run on the platform. And we also have low-code platforms, something we call Visual Builder, which lets you do very simple, little to no-code deployments for modern apps. Okay? Above that, we have a set of cloud-native services which are based on open source. It includes managed Kubernetes, again, a part of this typical modern app deployment architecture, and a container registry. We've got things like managed Terraform, so you can do easy spin-up of libraries and applications that you've designed, or third-party software components. And we have a fully serverless infrastructure called Oracle Functions Cloud Service. It's based on the open source FN project. We also have a fully integrated data platform. Now, this being Oracle, as you'd expect, we have our flagship autonomous database, right? But we also offer a whole range of database, open source databases like MySQL, third-party databases like we've started to support Microsoft SQL Server, NoSQL options, et cetera. All there is an integrated part of the platform. We have a serverless Apache Spark service that we call Dataflow that lets you do big data operations at scale, which can be particularly important for some of these intelligent applications where you're working on training models over very large data sets. We have an Apache Hadoop service, and data integration services for bringing data in, transforming it, doing data prep, which can be a precondition for the data science projects. All this can be managed in a data catalog. All these data assets can be tracked across the cloud, and all these data management systems, so you have an integrated view of the data assets that are in the system, who owns them, where they came from, et cetera. And then one level above that, for artificial intelligence, we have a rich set of services to make it very easy to build things like chatbots and digital assistants, to create machine learning models, and to build blockchain solutions. You can embed these machine learning models directly into your app using our data science cloud service. So it's all there as a complete platform. We think it's really the best offering in the market today to build these modern, intelligent, cloud-native applications. So we did this, we built this, and we designed it with 4 central principles in mind: open, modern, easy, and intelligent. Okay? So what do I mean by this? We're open in the sense that we don't lock you in. We use open source all over the place. We make open services. We generate a lot of our services based on open source capabilities that we're optimizing for the cloud environment. And we allow you to bring any kind of application development tool or platform into the cloud. There's a whole range of data management capabilities, so openness is key. We also have been focused very much on modern applications, right? Especially when it comes to modern architectures, modern deployment choices, and allowing you to take advantage of the serverless paradigm. And we're going to see some examples of that coming up. The Oracle Cloud makes it easy to get started in minutes. Easy to sign up. There's now a free tier for developers. You can get started today, right off the bat, and start using everything I'm talking about right here. And of course, we have a big focus on building intelligent apps. Apps that are powered by machine learning, that have advanced analytic capabilities. The platform itself, as I said, is optimized for HPC workloads. It's optimized for data science. And we have services like our data science offering that make it easy for teams of data scientists to work collaboratively, get their models into application consumable forms as APIs, and then manage those applications through the whole life cycle, where it may involve continuous retraining, redeployment as the data sets change and shift. So we definitely are proud of what we're offering here as a platform. I'm going to invite Todd Sharp up. So he's going to come up and give you an example of just how easy it is to build one of these intelligent cloud-native applications in practice. So Todd's one of our top developer advocates. He's super passionate about emerging technologies. And the app that he's built is one he did for himself, kind of near and dear to his heart. He'll tell you the story. But Todd, I'd like to invite you out, and you can take it away.
Thank you, Greg. I appreciate it. What's up, Code One? Nice. We're going to look at some really cool stuff today. But to give you a little background and context to this demo, I'd like to share a personal story, if that's OK. Before I do that, let me tell you a little bit about myself. As Greg said, I am a developer advocate for cloud and autonomous database here at Oracle. I live in the mountains of North Georgia with my beautiful wife of 17 years, my 13-year-old daughter, my 12-year-old son, a potbelly pig named Milton, 6 chickens, a dog, and a cat. Yeah, I think that's it. Yes, it can be kind of hectic at times, but we really love it, and we wouldn't trade it for the world. So today I'd like to tell you a story about my daughter, Ava. Ava is a typical 13-year-old girl for the most part. She's very smart. She's very mature, really organized. She gets that from her mother. She's involved in all kinds of activities like honors chorus, beta club, poultry judging. She's in archery. She can be kind of quiet and shy around new people, but really when she's around her friends and family, she's like honestly the goofiest, silliest girl you've ever met. But last spring and into summer, she started experiencing various symptoms that really at first seemed kind of unrelated to each other, and kind of just honestly seemed like just normal signs of adolescence at first. Things like being tired all the time, just kind of feeling crummy, always hungry, always thirsty. I mean, you don't think much of this when your teenager tells you that they're hungry all the time, right? Like I said, initially they weren't too concerning, but then she started like getting headaches all the time and complaining of blurry vision. So we started to get a little concerned at that point. It finally came to a point where my wife suspected that something bigger might be going on, so she made an appointment with Ava's doctor. The doctor did some blood tests and called us really quickly and said, hey, you need to get to the hospital. Ava's blood sugar is 475 milligrams per deciliter, which is much higher than the expected about 100 normal range. So that night, Ava was admitted into the hospital down at Children's Hospital of Atlanta, and she was diagnosed with type 1 diabetes. We spent the next 3 days in the hospital getting her blood sugar levels under control, and really the next few months just learning how to manage the disease. We're learning as much as we possibly can about diabetes and how to care for Ava and help her learn what it means to be diabetic and really just kind of listen to what her body is telling her. Most importantly, though, at least to me, we're trying to help her realize that diabetes doesn't define who she is. It's nothing that could have been prevented. It's nobody's fault that she became diabetic. It's just the challenge that she has to deal with now, and one that we really know that she can really overcome. When Ava was much younger, she had this school assignment where her teacher asked their students to write about their hero. And Ava chose me many years ago and created this drawing and wrote this little write-up about me. And it's something that I've kept, I'm sure many parents can relate. This is one of those things that you just keep forever and keep on your desk and just always cherish. But really the truth is, Ava's my hero. On that very first day that we were in the hospital back in July, she grabbed that insulin pen and just administered her own injection. And really ever since that day, she's taken every step that she needs to manage the disease and to continue to live her life as an otherwise healthy and happy teenager. I mean, her strength and just the courage that she's been showing has really inspired me to not let anything stand in my way. Now, she still has ups and downs, she always will, just as you'd expect, but her mother and her brother and I were just always going to be there to lift her up and encourage her to keep fighting. Oh, sorry. So what exactly is diabetes? I mean, everyone here has likely heard of it, and no doubt there are definitely people here that are affected by the disease in one way or another, either directly or indirectly. But just to clarify things, let's define it. Type 1 diabetes is an autoimmune disease that basically occurs when a person's pancreas stops producing insulin. And what insulin is a hormone that controls blood sugar levels. So diabetes develops when these beta cells in your pancreas are just destroyed by the body. It says, we don't need these, we're going to destroy these. So the body can no longer produce its own insulin. Diabetes can't be cured, but diabetics can manage the disease through diet, getting regular exercise, and receiving insulin. Now, every diabetic is different, but a typical day in the life of a diabetic might involve blood sugar levels being constantly monitored throughout the day. Now, many diabetics accomplish this via a little glucose meter like this that measures your blood sugar levels via a finger prick that's put onto a test strip. This happens at a minimum of 6 times a day. A lot of times more often than that, 8, 10, 12 times a day, every single day. Diabetics must count carbohydrates at every single meal and at most snacks. Now, it's really important to be as accurate as possible when doing this because they use this carbohydrate data along with their blood sugar levels to perform a calculation to determine the amount of insulin they need based on a personalized formula. And this formula may differ for every single meal of the day. Once the insulin dose is calculated, it's administered via injection with a needle or pen. And finally, diabetics have to be aware of and manage unexpected lows and highs throughout the day. Now, this routine is a reality for millions of diabetics every single day, without breaks, without any cheat days, no matter what, just to stay alive. Now, thankfully, technology has come a long way as it relates to diabetes management. If the diabetic is lucky enough to have the insurance coverage or to be able to afford these things, they may have the option to use continuous glucose monitors. These track glucose levels throughout the day via a tiny sensor wire that's inserted just below the skin. And they transmit those levels to a receiver or a smart device via Bluetooth, and they can share data via the cloud. Now, a CGM is often hidden by clothing, and so then obviously it's more discreet than manual monitoring. And honestly, nobody's going to suspect that a teenager that's looking at their phone is going to be checking their blood sugar level, right? I mean, they're probably texting a friend or something. Insulin pumps. Now, these deliver insulin doses, both constant and on demand, via a tiny tube that's inserted just below the skin. They provide a more reliable stream of insulin and are also more discreet than manual injections. They can also be controlled via smartphones and share data via the cloud. Artificial pancreas systems. To overly simplify things, an artificial pancreas is a system of hardware and software, CGM and a pump, that work together to deliver insulin as needed to keep blood sugar levels stable. Now, all of this technology can be life-changing for a diabetic by enabling them to spend much less time managing their diabetes and allowing them to focus their time and efforts on things other than diabetes. Now, as amazing as all this technology is, due to cost and other limitations, they simply aren't available or feasible for all patients. So what's missing? Well, with or without the technology, every diabetic must manually calculate their carbohydrate consumption and enter that value into an app or device to calculate their insulin dosage. This can be time-consuming and error-prone, which could lead to an under or overdose, and that's something that could really be devastating to a diabetic. And that's why I decided to build something to help simplify the process and increase the accuracy of carb counting. Let's take a look at a demo of the system that I built. All right. Okay. So let me make sure I'm connected here. It probably timed out as I was waiting in the back. Excellent. Okay. So everyone can see that? Great. So what we have here on the right side of the screen is the app running on my mobile device. And on the left side of the screen is just a camera I have set up on the table here. And I want to walk you through how to use the app. So what you see at the very top there is basically a mode selection buttons. And I built two modes, both a full mode and a quick mode. Full mode being including an insulin calculation, and quick mode if we just wanted to check the carbs in a certain piece of food and we didn't want to perform an insulin calculation. Below that, you can see all the various formulas. As I said, each diabetic has personalized formulas that sometimes differ throughout the day. So in this case, we have some different formulas set up. We'll go ahead and select lunch as the formula we use for the demo. And then at the bottom, we can choose a capture mode. We can either use a picture or a voice. Let's start off using a picture. So the next step here is the app's asking us what we're eating. And so at this point, we simply take a picture of whatever we're eating. So in this case, we'll take a picture of an apple. And we'll get that uploading. So let me get that out of the way here and bring in this guy. And what we have here is a Bluetooth digital scale. And at this point, the app's going to ask us to weigh the portion. So we take our apple. I've already paired the Bluetooth scale to the app, so I don't have to do that for this demo. But at this point, we simply put the apple on the scale, and it weighs the apple for us and updates the app in real time. So the next thing I'm going to do is accept that weight, so I'll just click the check button. At this point, the app is asking us to confirm what we're eating. It's identified that we're eating an apple, so we have a list of foods here to choose from, and we can, at this point, can choose apple raw. And the next step it's going to ask us is if we're eating anything else. So assuming, like I said, we're eating lunch, probably stands to reason that there'd be some kind of snack with lunch. So we have some graham cracker sticks here, so we'll say yes. And we will take a picture of the graham cracker sticks. Trying to get the glare off of that. There we go. I think that picture will hopefully work. And we'll pull the scale back over. Conference Wi-Fi is a little slow when uploading, of course. And there we go. So now we're going to weigh our Scooby snacks. As you can see, I'm not sure how well you can see it. It says 28 grams. The app's reporting 27.9, pretty close. We'll go ahead and confirm that. And it says which one of these best describes your food. Our first choice is Keebler Scooby-Doo Graham Cracker Sticks Cinnamon. Looks like what we're eating, so we'll confirm that. And the next step is we're going to go ahead and add one more thing to the meal. And in this case, we're going to add a peanut butter sandwich. Now, it would probably be pretty difficult to use image recognition to identify a peanut butter sandwich. It could probably guess sandwich, but it would probably have a real hard time guessing what's inside of that sandwich. It could be bologna or ham salad. So in this case, we're going to use our voice instead. So we switch over to the voice input screen, and we click the microphone. Peanut butter sandwich. All right, so it's taken my speech and converted it to text. We'll confirm that. We'll bring our scale back over here. We'll weigh our sandwich. 72 grams, sounds good. It asks us to confirm that it heard us correctly, peanut butter sandwich. And at this point, it's asking if we'd like to add another food. Well, no, I think a sandwich and an apple and some graham cracker sticks is a good lunch. So we're going to say no. The next step in the process here will be to check our blood sugar. Because as I said, not only do they need to count the carbs, but they also have to determine their blood sugar to determine their insulin dose. So at this point, we'll take this Contour glucose meter. We'll turn it on. And once it's turned on, we will pair it with the app. And it says our current blood sugar is 100, right? Because it read the app via Bluetooth. read the glucose meter from Bluetooth. This is my own blood sugar. I tested it a few nights ago. So obviously, I'm not being diabetic. I'm at about 100. So at this point, we've input all our foods, we've confirmed them, and we've uploaded our blood sugar. And the next step here is going to be to get a summary of our inputs. So if we click the check button now, we come to the summary screen, and it says, since your blood glucose is currently 100, you'll need a correction dose of 2 units of insulin based on your lunch formula. Your carb coverage is as follows. Apple, 192 grams, that's 26 grams of carbs, 2.21 units of insulin. The graham cracker sticks, we're at 20 carbs, and so on and so forth down the list of all the foods that are identified. And at the bottom, we have a summary of our total insulin dose of 8.45 units. We can save this meal by clicking the checkbox. And on the next screen, it tells us that based on the data you've provided, your next glucose reading is predicted to be 108 milligrams per deciliter. At this point, we click the checkbox, and we're done. Thank you. So let's take being a developer, and since this is Code 1, let's take a quick look at the architecture. At the heart of the system is a progressive web application, and that's what you just saw. The app can be installed and run on a laptop, desktop, or mobile device, and it's backed by 3 different microservices, all deployed as Docker containers in a Kubernetes cluster within Oracle Cloud. Having clicker problems today, and I apologize for that. This is probably why they want me to use their clicker. All right. Try it again. The user service stores information like target ranges and profile data in an autonomous DB instance, in this case, autonomous transaction processing. This instance is shared across all 3 microservices. Each of them have a distinct schema within that. I could have used separate instances if I wanted to, but just to keep things simple, I used the single autonomous instance. The user service is a Helidon SE Java microservice that handles persistence via Oracle REST data services, which is also known as ORDS. If you're not familiar with ORDS, it's a really awesome open source service that we offer. And I'd basically describe it as a way to get data in and out of Oracle DB using REST instead of SQL. It's really easy to configure, and it just gives you a simple API for persistence and querying. The next microservice is the formula service, and it's written as a Node.js microservice using the Express framework. Now, this service handles the persistence operations for the user-specific formulas that are used in calculating the insulin dosages. And for this service, I decided to store the data as JSON documents in Autonomous DB using SODA. And SODA stands for Simple Oracle Data Access. SODA is basically a set of NoSQL-style APIs that let you create and store collections of JSON documents in Oracle DB. You don't need to know SQL. You don't need to know how they're stored in the database. It just handles all that for you. The final microservice is the nutrition service. Now, this service is also powered by Java, but this time it uses the Micronaut framework. And for persistence, it uses Micronaut Data JDBC. Micronaut Data is it's a data access toolkit that uses AOT compilation, just like Micronaut, the framework does, to pre-compute queries for a repository interface that are then executed by this just really thin layer at runtime. Now, the nutrition service also provides an endpoint for image upload and also interacts with the USDA's Food Data Central API for nutrition information. Now, it's interesting to note that across all 3 of these microservices, there's only one SQL query used thanks to ORDS and SODA and Micronaut Data. A little more on that query later. Let's take a look at the food identification process in a little more detail. So how's the food actually identified? Well, as you saw in the demo, you can input foods via photo or voice, and depending on which method's chosen, something a little different happens on the back end. If a photo is used for food identification, it's uploaded to object storage, and a configured cloud event fires, which triggers a serverless function. So as you saw in Greg's talk, an FN serverless function. The serverless function performs the calls to several third-party APIs to perform the OCR and image recognition, and the results are published to a stream using Oracle Streaming Service. The nutrition microservice subscribes to that stream and posts the incoming message to a server-sent event endpoint that the PWA client subscribes to. This enables the results to be pushed in real time to the connected client without the need for polling or socket connections. Now this provides the front end with the image recognition concepts or the text that is extracted directly from the image, and that's used in the next step. The next step is to grab the nutrition information. If an image concept is identified, for example, like when we saw the apple, if the image recognition identifies a concept, but there's no text extracted, then the concept with the highest confidence value is used as a keyword for a search of the USDA's Food Data Central API, and that returns a list of potential foods. Now, of course, you can override that concept if the image recognition process wasn't perfect. But if the image did contain text, then that text, as in the case of the graham cracker sticks, is what's used as the basis of the query. The user then selects the food from the list of foods returned from the API, and the detailed nutritional information is retrieved, again, from Food Data Central. Now let's look now at how the next glucose reading is predicted. And for this, I used Oracle Machine Learning notebooks to construct and train a model for my predictions. Now, these notebooks are freely available with all Autonomous DB instances. It's kind of hard to see what's going on here, but essentially what happens in step one is that I use a query to create a single unified view of all the data that's going to be used to train the model. Now, to me, the beauty of this query is that even though I've stored the data in 3 distinct schemas, sometimes in a different model altogether, like JSON, as in the formula service, I still have the ability to combine all of the data in a familiar tabular view format via simple queries like this. Now, in this case, like I said, I combined the user data, the profile data, and the nutrition and meal data into a single materialized view. Next, we create our model. Now, I've chosen linear regression as the mining function here, but we offer many, many options as far as the algorithms that are available to you. That's just the one I happen to choose. The next step is to create our train and test data sets. We use a sample from the combined materialized view from step 1 to train, and the remainder of the data to test the model. Next, I make predictions against the test data with upper and lower bounds to determine the accuracy. And finally, I finish with the only SQL query used within the entire architecture, and that's the query that predicts the next glucose reading based on the inputs provided from the current meal. Now, I really believe what I've created in just a few short weeks can really be developed into something that makes carbohydrate counting much easier for many diabetics, especially those who are younger or maybe newly diagnosed. And while that's truly important, what I'd like to leave you with today is this. Everyone here in this room and those watching online have a really unique set of talents and skills and abilities. And we're living in the age of amazing technology. As you saw in Dr. Bourne's talk earlier, just access that we have is just amazing. Things like AI and ML are already doing so much to improve the lives of so many people with needs. But my challenge to you is this. Find something that is important to you. Something that you're truly passionate about. Maybe it's something that affects you directly. Or maybe it's something that affects someone you love. Maybe it affects total strangers. It really doesn't matter. But take advantage of the technology we have available and use your skills and abilities to do something to improve the lives of those affected by it. Let's do more than just build software for ERP or e-commerce. I mean, those things are great. Don't get me wrong, they put food on our tables. But let's do something to make this world a better place. Thank you. Next up, please welcome the lovely Maria Colgan. Thank you.
Wow, what an awesome demo. Hopefully you're inspired to make this world a better place. But what I'd like to do before we rush off and do that is explain how Todd was able to so easily store both unstructured and structured data and then process that data by taking advantage of the Oracle Autonomous Database. Now, that Oracle Autonomous Database is a new set of cloud services that are self-driving. That means that we'll automatically provision, manage, and monitor all of the infrastructure you need for that database, as well as the database itself. We'll make sure that it's perfectly safe by preventing any kind of external attack, as well as any malicious internal user that may be trying to get up to no good in your database. We also want to make sure that it's fully protected from any potential downtime. So we'll give you a highly available architecture as well as disaster recovery. Now, as Todd mentioned, he was able to use the Autonomous Database to store both his JSON documents, or his unstructured data, and his relational data, and then be able to join those data sets together. And regardless of what kind of language you want to use to interact with that database, you can do so with the Oracle Autonomous Database. So all the usual suspects, whether it's SQL, PL SQL, if you want to use Python, Node.js, .NET, whatever it may be, you can use all of those languages with it. Now, you can see there on the slide behind me all the different capabilities the Oracle Autonomous Database has, but rather than talking you through them all, I thought it would be great if we could take an opportunity to show you the Autonomous Database in action. So the first thing when you are starting a new project is we need to provision that infrastructure and that Oracle database. And oftentimes this can be kind of the long edge of the project as we wait for all of that to be deployed. And what I'm going to show you now is that we can deploy an autonomous database in just 2 minutes. So we're going to start that by logging into the OCI console. I can take one of the cheat shortcuts there, but I'm going to go the long way through the hamburger menu and pick the autonomous database off the list. Once I'm there, what I'm going to do is I'm actually going to change my region, so we're closer here to the Moscone. I'll go to the West region, and then I'm going to ask it to create an autonomous database for me. That opens a simple form, and I need to answer 5 or 6 short questions. First, it wants to know what name I want to give it, so I'm going to call it mine Swingbench ATP, because that's the workload I'm going to run against the database in just a minute. Next, once I've got the display name, it needs a database name. I'm going to use the same one. I'm not very imaginative. It's late after all in the afternoon. Next, I get to decide what type of workload I want. Am I going to be a data warehouse or transaction processing? I'm going to pick transaction processing, and I'm going to make sure that I get the serverless one where I don't worry about anything at all. Now I get to pick what resources I want for that database. You can have anywhere from 1 to 128 CPUs. I'm going to have 2. And the same with the storage, anywhere from 1 to 128 terabytes. Again, I'm going to just go with 1. I could enable auto-scaling at this point to let Oracle scale it for me, but I'm going to show you how to do it manually later, so let's not do that. Next, I need to give it an admin password. You see there in red, Oracle specifies a bunch of rules that your passwords must meet. Once my password meets those, though, it disappears. Last, I need to decide on the license. Am I going to bring my own license or pay for a license as part of the service? I work for Oracle, so I'm just going to bring mine. And with that, it will instantly begin to provision that autonomous database for me. And what it'll do is open a new console that shows me all the information and all the controls I have for that autonomous database, whether I want to stop it, start it, scale it up. You see there information about the decisions I made when I began to provision that system. And at the bottom of the screen, you'll see information about backups. Your autonomous database will be automatically backed up on a nightly basis for you, and we'll keep 60 days worth of backups automatically for you. You can also take a manual backup, so if you're making changes to the application and you want to be able to fall back, you can. And with that, I have an autonomous database, so that's pretty neat. Now, once I've got that database, I want to be able to connect to it. And with the Oracle Autonomous Database, you're going to get 5 predefined services that are going to help automate your workload prioritization. Each service has a different priority, so my mission-critical workloads can come in on that highest priority service. In this case, that would be TP Urgent. But if I'm running also analytics, maybe I'm running some reporting on that same system, I can have those queries come in at a lower priority service so that they don't interfere with the online users. I can also have some of that batch reporting run in parallel if I wish by using the appropriate service for parallelism. Once I begin to develop my application, one of the things that I might want help with is actually tuning or optimizing the database for that particular workload. And with the Autonomous Database, I'm going to get automatic indexing built in. And what that is an expert system that's going to monitor the workload. So as I begin to develop the application, I begin to issue queries against that database, it's going to monitor that workload for me, determine if there are any missing indexes from my schema, and then it will verify that if those missing indexes were present, that they would actually improve the performance of that application. So they would actually be able to speed things up. Once it's identified those indexes and verified that they do improve performance, it'll automatically publish those indexes to the application, and it can begin to use them and take advantage, excuse me, of that faster access method. Again, all of this happens automatically. You don't need to do anything in order for this to take place. It will just do it for it. And as your application evolves, let's imagine at the beginning we were going after certain data that actually we decided wasn't that important, and we've changed the queries over time. Automatic indexing goes in and cleans up after itself. So if an index it has created is no longer necessary, then it will just remove that index as well, making sure that we don't just bloat your database for you. Now, one of the things we touched on when we were provisioning our autonomous database was scaling that system. And with the Oracle Autonomous Database, there's really no rules around the scaling. You're free to scale either the CPU, the storage, completely independent of one another. So there's no fixed shapes that you have to adhere to, because no 2 applications are really identical. Oftentimes, some need more storage, while others may need more CPU, or you can scale both together. You can also take advantage of our auto-scaling, where you want Oracle to automatically scale up the resources for the system based on your workload. So you define a base CPU count, and then as your workload increases and you begin to max out that CPU, auto-scaling will increase the number of processors on that system automatically for you up to 3x that base number. And once the workload goes down again, we'll automatically scale you back to that base, allowing you to truly only pay for the resources you need when you need them. So how does that scaling work? Well, what I'm going to do is I'm going to run a swing bench workload here. I'm going to connect 128 users to my autonomous database. They're processing JSON documents, so inserting, updating, and retrieving JSON documents. And the 4th column there is the one that you're interested in. That's going to show you the transactions per second on this workload. So all 128 users are connected. And if you look at my transaction rate, you'll realize it's quite erratic, which is an indication that perhaps I may have overloaded my autonomous database. Remember, I only have 2 CPUs on that database. And so if I look at the database monitor to see what's going on, I realize I'm completely CPU bound, and the scheduler is working overtime trying to schedule all of my processes. So let's give it a hand. I'm going to go back over to the OCI console, and I'm going to scale it up. And I'm going to change it from the original 2 CPUs to 8. So again, could have the option to do auto-scaling, but I won't. I'm going to continue to do it manually. And what you'll see there is instantly, it'll begin to provision those additional CPUs for me. Now, if we go back over to Swing Bench, we'll be able to see that change take place. Now, it'll take a couple of seconds, about 20 to 30 seconds, for those additional CPUs to come online. So if you look at the monitor, if you can see it closely there, there's a dotted green line that indicates the CPU count. There it goes. It jumps up from 2 to 8. So we now have all 8 CPUs available to the service. And if you look at the 4th column across in the background there, my transactions per second is much more consistent now. I'm getting a consistent 32,000 transactions a second on my workload now that I've scaled the system up, which makes it nice and easy for me. Once I've got my development environment up and running, I may want to share it. Oftentimes, we're asked to clone dev environments. Maybe it's so that people can begin testing the application, or simply to allow a colleague to participate in it. And with the Oracle Autonomous Database, we make it incredibly easy for you to be able to do that by allowing you to clone that autonomous database and get a point-in-time copy of that database for a colleague or for that test environment. When it comes to cloning, you get 2 options. You can do a full database clone, one where you get all of the data and all of the metadata in the existing autonomous database over in the copy, or we can just copy the metadata. So the copy would have the exact same schema, the same users, but none of the data from production in it. You get that choice. It's super easy to clone. I'm going to show you an example right now, because all I've got to do is answer 4 simple questions, and it will automatically provision that clone for me. So here we are back on my database with the 8 CPUs and the 1 terabyte worth of storage. I'm going to create a clone, and as I said, your first choice is, do you want a full clone or a metadata-only clone? I'm going to go with a full clone. I want to give the developers all of the data, not just the metadata. Once I've made that choice, I'm going to scroll down, and it's already given me a default name for my clone, but I'm going to call it something a little more unique. I'm going to call mine Swingbench 2. I need to give it a new database name because it is a separate database, so I'm going to call it Swingbench ATP2. And then I get to decide, do I want to give that clone the same resources I had on my original environment or not? And this time, I'm not going to give it the same resources. I'm only going to give it 2 CPUs, but I am going to enable auto-scaling for it. I need to give the clone a new password. Same password rules apply. Once I've confirmed that password, again, I make a decision about licensing. I'm just going to bring my own. And straight away, I got brought into the clone UI now. So I'm inside the clone. You see the same general information about the clone as we had for the original database. And if I go out to the higher level view, you see there now I have 2 autonomous databases. The original autonomous database that we had, that's highly available, or sorry, currently available, and has 8 CPUs, and the clone that's currently provisioning with just 2 CPUs. If we go back in there, you'll see I have enabled auto-scaling for that clone, so it will actually be able to use all the way up to 6 CPUs. Oh, there it is. Now the clone is available. And just like my original database, that clone is a multi-model database, so it will be able to do structured, unstructured data, traditional transaction processing or analytics, as well as perhaps some of the newer generation type of applications, whether that's machine learning, as you saw Todd use, whether you're doing it as part of a big data environment, or perhaps as microservices. The autonomous databases make great databases for microservices. Regardless of what you're doing, you can do it with no risk and no compromise, because you're getting an autonomous database on the best platform for the Oracle database, which of course is Exadata, and you'll have all the scalability, availability, and security you're going to need for that project. Not only do you get all of that goodness with the Oracle Autonomous Database, but right out of the box with it, you're going to get a number of development tools to make it easier for you to get started with new projects. You're going to get SQL Developer Web, which has all the goodness of the Oracle SQL Developer desktop tool in a web browser. So I'm able to execute SQL, PL SQL through that. I'm able to build out my data models through their modeler capabilities. And I'm also able to monitor and manage that database through the SQL Developer Web. I'm also going to get an Apex environment. Apex is a web-based, low-code application development environment that it comes out of the box with your autonomous database. That way, all of your development can all happen within the browser and then have it instantly deploy against our autonomous database. We also allow you the ability to REST enable that autonomous database. So you can REST enable the schema and automatically generate REST endpoints for the tables and views within that schema, allowing your application to be much easier and simpler to deploy by simply making REST calls instead of having to write all of the SQL in the application. So let me quickly show you where you can find all of these tools. In the Service Console, you saw Todd go here earlier. Under the Development tab, there you see direct links to the Apex environment, the SQL Dev Web, the ML notebook that Todd used. I'm going to go into SQL Dev Web first. Here I'm going to log in using the admin user and the password I used when I created the autonomous database. Once I'm in, I'm there in the SQL workbook or sheet where I can write any SQL. I also have a home tab, which gives me information on the other activities I've already done in this environment. Or I can go into Data Modeler. And you'll notice when I go into Data Modeler, there's a little tour there that I can take to help you navigate through it if you wish. Now, I'm not going to do that right now. I'm going to create a user so I can get going on a new Apex application. So I'm going to go ahead, create that user, and grant it all of the necessary privileges it's going to need to be able to build the app that I want. So you see there at the bottom of the screen, you can see the results of that script output. I've got my user, so I'm going to go back over now and go into Apex. Again, I'm going to log in initially as the admin user, and I'm going to create a new workspace for the user I just created, so for my Apex dev. Now, you see, I could have created the user here as part of that screen, but I wanted to show you SQL Dev Web. But now that I have the workspace, I can begin creating a new application, and I can create additional workspaces as well. And it's not just the database that Oracle has turned into an autonomous database. You would have heard yesterday from Mr. Ellison all about Oracle Autonomous Linux, which allows us to automate the entire OS lifecycle for you so that you can stay current, because we're going to automatically patch and tune and look after that operating system for you, allowing you to be able to develop much faster without requiring any downtime in order to allow IT to patch your environments, and then requiring you to double check after the patch that everything has come back up correctly. We'll do it all online, fully automatic for you, so that you're always in a reliable and secure environment, but you're not suffering any kind of downtime in order to create such an environment. With that, I want to thank you all for joining me, and I want to strongly encourage you to take advantage of the new free tier that we have. Remember, you're going to get 2 autonomous databases as part of that free tier. You also have, remember, a special 30-day free trial just for being an attendee here at Code One. And again, I urge you to take advantage of that. And with that, I'd just like to thank you on behalf of myself and all the other speakers here today, and we hope you enjoy the rest of the show. Thank you very much.